Resume the session of Dr. Garfred, and he will be taking this session on impact assessment. So I invite Dr. Garfred, please.
Okay, welcome back from lunch. You had a short lunch, I assume, yeah. But anyway, good afternoon. Now we are talking about the impact assessment, and we've learned before lunch that the inventory analysis, this is really based on physical units. Yeah? So everything you use in the inventory analysis is based on physical uses, on volumes, on grams, on liters, on square meters, and so on. But if we now go to the impact assessment, we are facing units you cannot really measure because they are at least not a real physical units. Yeah, and what you see here on the left-hand side, these are really from the life cycle inventory, the CO2 emissions, the toxic emissions, the water inputs, and the other emissions. And we've already seen yesterday these different ways towards further summarizing more and more of these impacts into several categories. And the first step is this midpoint score impact categories. Yeah, and most relevant one is here, of course, climate change, land use, water use, but also human toxicity and other impacts. So this is a midpoint impact category or midpoint indicators, but you can further aggregate them to human health, to ecosystem quality, and natural resources. And as you can imagine, it's not so easy to combine climate change, human toxicity, other impacts into one category because at least physically in the inventory they describe totally different things. Yeah, then you first aggregate it to specific categories. Climate change is a global phenomenon. Human toxicity is a very local phenomenon. Yeah, and to combine these, of course, this is a very sophisticated thing on one hand, and even then to summarize three endpoint categories into a single number. Yeah? On the very first lesson on Monday morning, I told you sustainability cannot be measured in one single unit. And nevertheless, people try to do it, yeah? Because it looks, it might look or might be, of course, attractive to have only one number for all environmental effects. And if this number is higher or lower than something else, of course, that would be a relatively easy way. Um, on the other hand, if you look on the different environmental impacts, you can also categorize them, uh, what is affected by them. Yeah, and there are some indicators that are really relevant on a global scale, like resource depletion or emission of greenhouse gases, climate change. So wherever you emit greenhouse gases, if in Austria or here in India, at least they end up in the atmosphere and make global warming, and the whole planet is affected. In contrary, on a local level, for example, human toxicity really happens on a very local level. Yeah? So if you emit toxic emissions here in India, we in Austria don't care, more or less. Yeah? And and in between, there are some effects, regional effects, like acidification, photochemical ozone creation, smoke formation, and and at least these different impacts are relevant for different impact categories and for different local and geographical regions. And and since a long time, there's a long discussion going on if life cycle assessment can, should, or might really address all possible impacts. Yeah? Or if life cycle assessment maybe is best only to address global issues. I give you a simple example. If you have a car driving by, from the stack emission, there are toxic emissions involved. Yeah? If you directly put your nose on the stack, that's a problem. But if you pass by in a 3 meters distance, you're not so much affected. And even if you're 100 meters away, yeah. So it very much depends where is emission source and where am I? Yeah. And this is in all the modeling of human toxicity a very, very difficult thing. Yeah? Or if you think on a long stack of a power plant and that emits in 80 meters high some substances, and they are at least very broadly spread, so the concentration, at least that ends up in my nose, is relatively small. Yeah? And this is at least the difficulty with these local and regional, but mainly local effects, that they are depending on where you are. Yeah? It's the same with biodiversity. So if you go to a farmer, on each square meter, not each square meter, but from place to place, the biodiversity is different. Yeah, here you have more water, here you have more stone, here is a tree. Yes, so even biodiversity is so depending on where you are. Yeah, and if you change something, and even how do we count biodiversity? Is it the number of different species, or is it the number of one species? Yeah. So it's also very difficult to measure that on a reasonable, mainly science-based way. And we have seen that Professor Singh, that was very nice that he pointed out and showed you all the results. If you really try to go to these really endpoint indicators here, yeah, and you've seen the units he used there. Maybe you have never seen them before. So we at Ioneum, we have at least we do contract research, and of course we always have to see what is also the interest of our clients, and most of the clients we're doing LCAs, they're interested in the global impact categories, yeah, because they are the key elements in environmental protection. That does not mean that the others are not relevant, but there's a discussion if life cycle assessment is the right methodology to address human toxicity or to address biodiversity. Some guys say biodiversity is important, but you have to talk to the farmers. You have to talk to agriculture. You have to talk to forestry, yeah? Because they in their daily life are relevant for biodiversity. But for the feedstock I get from them, finally in the LCA you find out that biodiversity is only relevant, mainly relevant for the cultivation stage. And so it's not a question, it's really a question if life cycle assessment methodology is really appropriate to cover or to address all these different issues and impact categories. And even as they are so complicated, yeah, what is not yet covered from these categories, this is part of my current research work I'm performing, is there is no indicator that somehow measures climate neutrality. Yeah, they measure global climate change, but none is really addressing the climate neutrality potential or the circularity potential. So how much of the mass is really kept in the cycle? Yeah, even all these resource indicators don't give you an information how much the material is really kept in a cycle, and and therefore we have in a big research international research project with 14 countries, we have developed indicators for this climate neutrality and circularity. I address a little bit later on, and maybe in future you will also find some indicators on climate neutrality and circularity on this list. And now I show you just two slides where these, I think there's 15 different impact categories. In Europe, we had 10 years ago a big initiative on environmental um, product environmental footprint, that for each product you really analyze all these aspects. It did not really work because it was a relatively complex activity so far, but they have identified this list you have seen already from Professor Singh. Climate change, ozone depletion, human toxicity is split up in cancer and non-cancer effects. Yeah? And they have the unit, the CTUH. I always have to look up comparative toxic units, yeah, for human health. For ecosystem, it has an E on the back. So these are very complicated mechanisms to come from the original emission to these impacts. And And for example, for particle matters, they also do a same concept to have an equivalent substance, like for the CO2 equivalent, they have the CO2, and for the particle matter, they have the particle matters with 2.5 nanometers in size, and what their damage is, they use that as an equivalent factor for other particle emissions. But anyway, this is the list is even longer. Um, Different units, most of them have an equivalent factor, yeah, and this equivalent factor is a tricky thing because um, to know for global warming, for the global warming gases, you have relatively good information how they change the radiation if they're in the atmosphere, how they influence the long and the short wave radiation, which makes global warming. But for the other equivalents, it's even more difficult to identify in comparison to reference substance how much they contribute to marine eutrophication, for example, or freshwater eutrophication. So as you hear from my description, I'm a little bit skeptical if it's really uh, necessary or really scientifically sounding to address all these different effects. Or in other words, as I'm working in applied research, I would say that the global indicators, they are already well developed, and maybe the others will finalize their development in future, and that you get all these categories. But when you want to calculate all these 15 impact categories, you also need tremendously more data in the inventory phase. Yeah, because for all these things, you need many specific emissions. Yeah, even from wastewater and from water demand and from the different emissions. So it also makes the data collection even more complex. As I already said this morning in the goal and scope part of the LCA, which is a starting point, of course, you can decide which of these effects is the most relevant you're analyzing. But if you only analyze one impact category, you don't get a good answer. Yeah? Because if you only look on one, there's always a winner and a loser. Yeah? So in principle, you should do minimum two. Minimum two. And that's what we say you need on one hand the greenhouse gases you see here on the left hand side, and on the other side the primary energy demand. And as you see on the results here, if you only look here on the left-hand side, on the right-hand side, you always find a winner. Yeah. And what you see here is an electric car, a hydrogen car, an e-fuel car, a diesel, and a petrol car driving 1 kilometer and giving you the CO2 emissions per kilometer. Yeah, and you see here that the green one, the blue one, and the red one, they have roughly the same greenhouse gas emissions. Yeah, so it looks that the electric car, the hydrogen car, and the e-fuel car has roughly the same greenhouse gas emissions, which is true if the energy source in that case is based on wind. But on the right-hand side, you see how much primary energy do you need to drive 1 kilometer. So this is a factor on energy efficiency. You see here clearly that the green one, the electric battery car, has the highest efficiency. So you need the lowest amount of primary energy to drive 1 kilometer. Yeah, the hydrogen car even needs the double amount already because of the conversion efficiency. First you make from electricity hydrogen in the electrolyzer, and then in the fuel cell you convert the hydrogen back to electricity. And in total you lose 50% of the energy. And here you see that the hydrogen car needs the double amount of energy. And the red ones here, the e-fuels, you see they need 4 or 5 times more energy because they're starting with water and CO2. I explained you also on Monday morning. So at least it's very important to also have the same systems compared, looking on the primary energy demand. So my recommendation is at least you need these two minimum categories to get an information. And the tricky thing is to judge overall. Yeah, if you see it with your left eye or with your right eye, what is really the most relevant one. In this case, there's still a winner because the green one is best in two cases. But I'll show you later on also one example where you see it's sometimes not so easy if you compare to different things. And now imagine you have these graphs not only for 2 impact categories, if you have them for 15, and they go once like this and once like this. So it's really, it makes it really complex to find at least what is the best one, or the most sustainable one, the most environmental one. Um, one very important is this primary energy demand. Very often in the English language they call it cumulative energy demand, which is at least the same. Primary energy means it's really the energy you take from nature. Yeah, so it's the wind, it's the sun, it's the water, it's the biomass, the heating value of the biomass that's grown on the field. This is the starting point, because this is the amount of energy you take from nature and you transform it to a transportation service, for example. Yeah, and the question is how much of this energy you need is then at least the definition of the primary energy demand, and it's normally reported in megajoule or gigajoule, depending on the orders of magnitude you're asking. And it's really the primary energy, and the primary energy has to be distinguished between non-renewable and renewable feedstocks. Yeah, so our energy carriers. That's also important because the renewables they come again and again, and the fossil and the nuclear they disappear sooner or later. And this is also very important for the final judgment on the cumulative energy demand, to see which energy carriers are involved. And also the heating value in the feedstock is part of the cumulative primary energy demand. So if you extract raw oil, it has a heating value that is at least the primary energy you put into a system driving on gasoline or diesel. Or if you have biomass, wood or grain starting, so it's the heating value from the very beginning you start to operate your system. Um, and then you see at least the list up there is just a more detailed list of the different energy carriers, because normally if you look in databases on the primary energy demand in this complex process chain, at least all energy carriers are somehow involved, yeah, because the system is so complex over different processes. So at least you have a relatively long list of possible primary energy carriers within the system. Finally, there's one distinction: the primary energy in the I think in America, I don't know how it is in India, but in America, normally they calculate with a higher heating value in all of their calculations. Yeah. We in Europe, and I don't know how you handle this here in India, we calculate always with the lower heating value. And the difference is only the energy from the water vapor you create when you burn something. And so also for the primary energy demand, you have to say I'm referring always to the lower heating value, or I'm always referring to the higher heating value. The good databases, they switch. You can tick what you want to have, but of course you should not mix it to be consistent. But we do that in yeah. I just show you two examples. When you get a result on the primary energy demand, this is a system that provides you heat. So it tells you how many kilowatt hours of primary energy you need to heat a house, for example. Yeah? And one is based on wood chips, and one is based on natural gas. And if you see here that the natural gas, the value 1.4 is a little bit lower than 1.5. And that means the system using natural gas in terms of primary energy, in terms of energy efficiency, is a little bit better than the wood chips, which is a fact, which is true. But it's also relevant to see, okay, but more than 90% in one case is renewable, and more than 90% in the natural gas case is not renewable. So therefore, in your judgment, you say, okay, we want to reduce fossil energy, we want to introduce renewable energy. Maybe it's okay if you need a little bit more of energy, but the big share is really renewable, and we're reducing the share of fossil energy, because this is also a key target, reducing fossil energy. So for the interpretation of the result, which is the last phase in life cycle assessment, you need this information. So if you only count the fossil energy, you are not able in the interpretation to really draw the right adequate conclusions. So it's always necessary really to have the, the overall picture. One tricky thing is with the electricity consumption and the primary energy demand. Here's one example about paper making. Yeah? And if they make paper in Sweden, they need 3.4 megawatt hours per ton of paper. And if you do a recycling in Germany, you roughly need 1 megawatt hour per ton of pulp. Yeah? So you might say, looking just on the electricity generation, it seems that the paper recycling is 3 times more energy efficient than fresh fibers. But you have to also calculate back. In Sweden, it's mainly hydropower used for electricity. And the primary energy demand is 3.6. With the grid losses, when you calculate back, you end up with 3.6 megawatt hours per ton of pulp in terms of primary energy. Whereas in Germany, they still, it's a little bit an older slide, they have switched down nuclear yet, but still they use a high share of coal, they use a high share of natural gas and of nuclear. So finally, on the primary energy side, yeah, Germany has 5.3 megawatt hours per ton. Because here the efficiency of the thermal power plants is integrated. So if you want to have 1 megawatt hour of electricity, you need 4 megawatt or 3 megawatt hours of primary energy. Yeah. So with the electricity, of course, primary energy always takes the conversions into account, and therefore it's really important not to compare it on an electricity level. Yeah, saying this is more energy efficient. You always have to go back to the primary energy demand. Yeah, that's why it's so important to have this, because that's the only matrix to measure on energy efficiency. And we heard Monday morning, energy efficiency is a key in all sectors to reach our goals on climate saving, on reduction on greenhouse gases, is energy efficiency. Okay, I'm coming back to the indicators, really addressing more adequately maybe the global warming and the circularity. And if you want to face these two challenges, you have to develop LCA also a step forward. We call it a so-called dynamic life cycle assessment, which is at least the conventional LCA. I think you got a clue what is LCA, and the dynamic LCA is still an LCA. The only difference is that you also consider on the timing axis when the emissions occur. Yeah? Do they occur on the very beginning when you build the system? Do they occur when you use the system? Or do they occur on the end of life? This is the only difference, that the timing of the emissions, but also the timing when do you extract material, when do you recycle material, is part of this dynamic life cycle assessment. And I show you this graph again. We have seen already for these two systems A and B, we have seen that already. And this system C is currently the most relevant in our daily research at Joanneum Research, because this system C has high emissions maybe on the beginning, but during the lifetime, there's not very much additional accumulation because the line gets flat. And a very good example is when you have an electric car that lasts for maybe 10 or 15 years, if I plug in today, I get a different electricity mix compared if I plug it in 5 years or in 10 years. So during the lifetime, during this red phase here, the electricity mix is changing. For example, in Austria, we currently have 70% renewable electricity, but we have a national goal of having 100% renewable electricity already by 2030. Yeah? So that means if I plug in now, I still get fossil electricity, but maybe in 10 and 15 years, I only get renewable electricity. So at least adding no more greenhouse gases, yeah, but still having the transportation service, yeah. And this is for us a quite interesting thing, because if we find systems that at least in that phase, 2/3 of this phase, we have no further emissions, but still a transportation service. And we say, okay, this goes in the right direction. It's not climate neutral, but you still have emissions, but it's going towards climate neutrality because you don't add more emissions. Yeah? So this is relevant, and then we have the case that the on the very end the the curve is going down. We talked about that already the day before. If the green line here is the extraction of material or the materials you need to run the system C. In the production phase, you have to extract them from ground, so it's primary material. Then during the phase, maybe you need some spare parts or things, also some material inputs. But on the end of life, it goes down, because if you're able to recycle or reuse most of the material, yeah, then it's good, because then you're closer to circularity than throwing everything away or put it into landfill. And that's why this is also on the end of life very relevant for this circularity assessment, and we have to try to put materials more in a cycle, and with that you also have a possibility to measure circularity. And with that, and finally everybody is talking about climate neutrality. Yeah? And I tell you that no system is really climate neutral so far. So all we do has more or less impacts on climate, on global warming. The only thing we can imagine is this dotted line here describes a system for carbon capture and storage. Yeah, that means you filter out the CO2 from the air, you compress it, and press it in the ground and close it perfectly that it does not emit anymore. This is carbon capture and storage, which is a technology which is in some areas it's tested, and it's one way also in the oil industry to press back the CO2 to get out more oil or gas. But in that case, it's really to filter out the CO2 you emit with your system and store it underground forever. Of course, you need energy to do so, yeah, because you need to suck out the CO2. But in theory, if you have in parallel with the green system, this carbon capture and storage system, so all the time when the green system emits greenhouse gas, the carbon capture takes it. So there's no increase in the atmosphere, because if at the same time you put it in and put it out, you're really, really climate neutral. And this is the only visionary idea, more or less, or say this, then this really could be a fully climate neutral system over the whole lifetime. Yeah, and this is also something we are targeting to. Okay, having said that, uh, we have developed a definition that can be applied to life cycle assessment to define climate neutrality and circularity. And to a certain degree, they are combined. Yeah? We define a 100% climate neutral and circular system can defined in two different ways. Yeah? If you're an optimistic person, you say, yes, I only use secondary material. Yes, I only use renewable energy. And yes, on the very end, everything is recycled. So these are the three principles: secondary material, renewable energy, and 100% recycling. You can say the same thing if you're more a pessimist. You say no primary materials, no fossil energy, and no landfill, no waste. Yeah? This sounds relatively simple, yeah? And this is at least written here. But really, if you have a system using only renewable energy and only secondary resources, then you have an ideal case of 100% circularity, which in reality is also very visionary. But with this definition, we are really able to measure circularity with a circularity potential. I'll show you a few slides later, and also in combination, also the climate neutrality potential. The circularity potential is based on the data from the inventory analysis, where we have all the mass flows. We know all the mass is going in and all the mass is going out. There we can at least use these data to judge the circularity potential. And the climate neutrality, we have calculated the greenhouse gas emissions, and they are the starting point to calculate the radiative forcing potential. I show you on the next slide to see how far we are towards reaching climate neutrality potential. Of course, I'm aware these definitions are very visionary. Yeah? These three yes or these three no's, that's quite visionary and maybe very long term. Yeah? But it's not the goal to reach already tomorrow 100% circular, 100% climate neutral system. That's not the thing. The more important thing is here that we have to assess all our products if they have the possibility to become climate neutral, if they have the possibility to have a higher circularity than the existing product. Yeah? So you have to assess all the products to see if they're at least towards climate neutrality and towards circularity. And this is at least the most interesting way to use these definitions to judge and compare different systems based on life cycle assessment. I show you why the climate neutrality potential is something different than the greenhouse gas emissions. You see here on the left-hand side, three different systems making electricity. One is photovoltaic, one is biomethane, one is a nuclear power plant. And you see here, the first time they are erected, then they have the operation phase, and then they have the end of life. And all the three systems end up on the very end with the totally same greenhouse gas emissions, assuming that during the operation phase, they have the same service and the same lifetime. So these three systems at least produce the same amount of electricity. And if you only look on the greenhouse gases, you say all these systems have the same grams CO2 per kilowatt hour, because on the very end they have the same greenhouse gas emissions. Yeah? So you find no difference. On the right-hand side, we have calculated this climate neutrality potential, because all the time when you emit greenhouse gases, you change the radiation behavior in the atmosphere. Yeah, so it tends to increase, it tends to warm up the planet. But we also see if we put CO2 in the atmosphere, the CO2 is decreasing, because a part of the CO2, a big part, disappears in the ocean. Yeah, and it has several things, and also the methane is deconstructed. So at least they are reduced in the atmosphere. Yeah, and you see here, for example, the photovoltaic has the biggest emissions when you produce it. That's clear, because if you put it in the sun is shining, you have no additional effects. Yeah, and as it emits on the very first time, it has in the beginning the highest radiation potential, but then due to the decrease of the emitted greenhouse gases, the blue line is going down. Yeah? Whereas the black line for nuclear has a little bit on the beginning, and if nuclear, maybe to dismantle a nuclear power plant and all the final storage of this material, maybe this is very energy intensive. Yeah? You see that the nuclear has the highest potential on the very end of the lifetime, and the biomethane is in between. Yeah? So this is the nice thing with this climate neutrality potential. You can also count on the timing when the emission occurs. Yeah? So in that case, it's good if the emission occurs now, because then on the long term, we really have a decreasing in the global temperature finally, yeah? Compared to a system where you have the emissions on the very end or even in the operation phase. And that's why we think that this climate neutrality potential is quite a very important thing to be integrated, because if you only look on greenhouse gases, you get an information, but in that case you see no difference, which does not reflect what you are interested in. And the other important thing is this circularity potential. We have used this material circularity index that was developed in the UK, and they say it's based on the mass balance, and it has two factors. One is a material specific factor for steel, for concrete, for copper, and it has to be combined with a utility factor. Yeah. And simple example is if you have 1 ton of steel and you make a car out of it and you use it for 12 to 15 years, yeah, that's one usage. If you have 1 ton of steel and you build a bridge and the bridge lasts for 100 years, yeah, it seems more reasonable because it lasts for 100 years. It's more or less the same ton of steel. So it seems to be more circular because you have a longer lifetime where you have this in use. And this is the basic idea behind this circularity potential. You have a material factor and a utilization factor. And with these two, you can at least measure the circularity, which is between a 0 and 100%. 100% means visionary, 100% circular. 0 means you throw everything away. Yeah? And so this is a possibility to really measure the circularity and compare the circularity on two different things. And here's one example on the we have a battery regulation in Europe because we have so many battery electric cars now. So they put a regulation in place that for the future batteries, we must use more secondary material when we make new batteries, and we have to increase the recycling on the end of life of the batteries. And the regulation gives you clear how much of the lithium, the cobalt, and the copper has to be recycled. And when you use these data, you see that the current battery produced in Europe roughly has a circularity of 40%. But in the years to come, in 10 years, when this regulation is fully implemented, you're more than 60%. Yeah? And this is this nice thing on this indicator. You see with which measures you're able to increase the circularity or the circularity potential of your product. And you can also apply this circularity thinking on the carbon cycle for all bioenergy systems, which is a little bit sophisticated, but still it works. And even there you need the timing because the CO2 uptake is depending on the photosynthesis. And this is my last my last slide on the visionary area, because the big question is always what is the vision ideal 100% sustainable transportation system. And that would be when you say you have a certain mobility demand which is influenced by different factors, and then you ask a certain transportation service, and then the technical system starts, because mobility starts not in a technical system, it's influenced by us. We also discussed that already. And then you have the transportation service where you really have the materials involved. And in an ideal case, all the materials go in a circle again and again. Yeah? So nothing is lost. So you always redesign, remanufacture, make, use, repair, refurbish, recycle, recover. So this is the ideal case. And this cycle is running in around because you feed it with only renewable energy. Yeah? So this is the idea. Which might be also a guiding principle for us in future to develop systems that are close to this. And with this circularity and climate neutrality potential, we are really able how far we are always with our system towards this at least visionary goal. At least coming back, you see this picture again, because this is the basic framework of LCA. So if you start doing in the LCA, you're covering these 4 elements: the goal and the scope, the inventory, and the impact assessment. And now I'm touching a little bit on this interpretation. Yeah. So what to do with the results you get on the very end. And I should give you a relatively simple example. We are comparing 2 systems, the system A and the system B, and we have decided to look on 4 different inventory categories: CO2 emission, the fossil energy, the agricultural area demand or area occupation, and the particle emission in a specific site. Yeah. And they're all normalized. Both systems provide the same service. And here you find the units in tons or in megawatt hours per year. And you see here the system A is good in 2 categories. The green one is good and the red one is bad. And the system B is good in the other 2 categories, yeah? And vice versa. And now you have spent much time on getting these results and you're very proud and happy to have all these numbers. But which system is better now? Yeah? Do you have a clear clue which system is really, really better? What can you recommend? What shall we do? Some guys say we can summarize, just make it a sum, because they are all numbers. Yeah, you're smiling. Yeah, it's not possible because the units are different. Yeah? But in I don't want to be ironic, but some impact categories somehow try at least to summarize different units. Yeah, if you compare global warming and human toxicity in an endpoint indicator, yeah, you're summarizing up totally different things. One is human toxicity; it's about my health, and the other one is heating up the planet. And to bring that together is also a kind of summarizing, not so simple as it looks here. So it's more sophisticated, but still, I'm very much in doubt um, to summarize that in any way. Yeah. So what to do? What to do? It's also showing you this is at least also the limit what LCA on a scientific base can do and what it cannot do. Yeah? And you have to think about it. This is the basis to start a discussion. It's a basis to start a discussion because sustainability is more than only the environmental part. Yeah? It also has a social dimension, which means talking to each other and considering for my specific application um, to see, okay, if I take the system A, I have I'm reducing greenhouse gases, but I'm increasing my particle emissions. Huh? In system B, I know I'm increasing my CO2 emissions, but I have lower particle emissions. And then you can say, okay, if I'm in an area, Graz, for example, where we came from, we have a high air pollution problem because we're in a basin and we have bad air quality because the wind is not cleaning uh, the city. There, you really have a problem if you add additional dust in the atmosphere. Yeah, yeah. So at least maybe for a city in Graz, it might be better to choose the system B with the lower particle emissions. But we have the information. If we do so, on the end of the year, we have increased the greenhouse gas emissions. Yeah? If you're more in the countryside, yeah, you might say, okay, the particle emissions is a local phenomenon, and if the wind is blowing there, maybe you spread it already a little bit more, so it's not so dangerous to the people. So that then it's maybe good because there you can really reduce fossil energy and greenhouse gases. Yeah? And this is at least the most often case that you don't find a clear answer. Yeah, it's always a mixture, like we've discussed yesterday with the electric cars and the conventional cars. It's not a black and white picture. But you can imagine if you only consider the first two or the three or four, you might have a clear winner because you only look on two categories. Yeah? And if you choose the categories you think that that's good for my product, yeah, then it's really misleading. So again, it starts when you start defining the goal and the scope of your LCA. Which impact categories do you really include? Yeah, to be really objective. Yeah, and so at least you need minimum two. If you have four or five, it's even better. But it's really a tricky thing. And my personal opinion is that at least there's no scientific evident overall assessment category. So I'm very skeptical about this endpoint and one point indicator where you really think you can put all in one number. I don't believe that. There are many attempts doing so. Even life cycle experts are doing so, which is somehow okay. But I think they do simplify it, at least somehow trying to summarize things which are very difficult to be summarized. Yeah? And so I'm not. They use very specific. We've seen yesterday some of these units. We also have a big initiative in Austria. They count the global hectare, nobody can tell me what is a global hectare. I see a hectare in agriculture, in forestry, a parking lot, but not a global hectare. But they try to reduce all emissions and impacts on a square meter basis and the Umweltbelastungspunkte. So I'm very skeptical on this. I believe more that we look on single categories where we are really sure that we have a scientific good basis based on LCA to quantify greenhouse gases, to quantify primary energy. And with the results, with this colorful table, this is the starting point to discuss with the people and to see what are the framework conditions. And in reality, everything has disadvantages and advantages. That's reality. Yeah, you always face that. And to be honest, we also think that this is LCA can provide data, and then you need a discussion, and you have to judge, and you have to make a weighting on the key effects. So I think, or in the LCAs I perform or we perform at Yoneum Research, we have this 4 or 5 main impact categories where we are really sure that the assessment works perfectly: the carbon footprinting, the energy footprint, the water footprint, the material footprint, the land footprint or the land occupation, and some air pollutants, the conventional one, the SO2, the NOx, the particles. This works. We think these are really good basic indicators, and especially for new technologies, you're also developing here pre-treatment methodologies and so on. I think with these categories already you cover quite relevant areas um, of the environmental side. In future, I'm quite sure that the climate neutrality potential and circularity potential will also be on that list. We are currently started a longer discussion on how to include that also in life cycle assessment, because we think these are really two new impact categories. And my last 3 slides, they will again go back and bring a little bit light on land use and land use effects, because biomass, if you use biogenic resources, you always need land. Yeah? You need land which is occupied with crops, with grassland, with trees, and in that it's always relevant how much land, which type of land you really need in for your different technologies. And the story on land is a very long story. I will tell you tomorrow even additional aspects. But finally, it's relevant for today to know the one thing is how much land you need. So you occupy land for a certain time. You don't use land because the land remains the same, but you occupy it because you plant something there. Yeah, you grow grains or you grow rapeseed or whatever. So you occupy the land for a certain time is one thing. And the other thing is that you also transform the land from, for example, from grassland to agricultural land. Yeah. So this is also relevant in terms of the carbon stored there. So the transformation of land is also relevant in the reference land use we see on biomass resources. And what I will tell you a little bit more in tomorrow is we have different land use change effects, the direct land use change effects that can be addressed in life cycle assessment. And there are also indirect land use change effects. I will explain tomorrow more in detail that cannot be measured with life cycle assessment. You need economic models behind that because they are not directly linked to the LCA, to the attributional LCA. We heard this morning. This is more about the not the consequential LCA approach, where the indirect land use change come into the game, which at least has nothing to do with life cycle assessment. Here I just briefly explain to you how you can describe the land use. So it's always running over time. So again, the x-axis is the time running. Yeah? So time is relevant in LCA also. And you start with a certain quality of land, with a certain amount of land, and a certain quality of land. And then you start to do something on that land, and it might be that the quality is going up, down, or being the same as long as you occupy this. So if you put a grain in there and before you have rapeseed, you change the quality of land during this time. Yeah, in forestry also, if you start to grow poplars, we heard this before lunch break. If you grow poplars on agricultural land, of course you change the quality of the land. The quality indicators is a very complex thing again. You have to measure the quality of land, but at least you change it in one direction. Then you use it a certain time, and when you stop the use, you might have a certain regeneration time. And the question is, do you reach the same quality afterwards again, or do you have a lower or a higher quality? So judging on the land quality and the changing of the land quality is a very relevant aspect. So one is really what's happening to the quality of land. Tomorrow we see one important indicator is how much carbon do you store by different uses on a piece of land. Yeah, and even in grassland you have more carbon than in agricultural land. In the forest you have more carbon per hectare than on grassland. So this is one thing. And in terms of LCA, when we talk about land use, it's not land use at least physically, it's a land occupation. Yeah, so you're asking how much land do I need for 1 year? Because normally you think in years because so this, I'm occupying a square meter per year. That is normally the unit to measure on land occupation. Um, I won't go through the list of the different indicators describing the quality of land, because this is not my expert area to go into this soil and land indicators. But the more you go into that, maybe it's also not so relevant, except for some N2O emissions, carbon content, which are directly relevant for LCA. Other criteria are maybe more relevant for the farmers, for the agricultural sector, to discuss the different things. But I have to mention there are many, that there are tools that are really able to use different soil parameters and to really model the changing of the soil when you put there different raw material production systems. Yeah, so there exist models that have a very detailed modeling, but they also are quite data intensive. Yeah, because you need all the data for each hectare of land to really run these systems. Yeah, and to see how the quality of land is changing. But anywhere you have to be aware, quality of land is a relevant issue when we use biogenic resources. So this is the summary, the take-home message for today from my side. We've seen there are many different environmental impacts, and they affect the global scale, the regional scale, or the local scale. The indicators on the global scale, I think the methodology of life cycle assessment suits very well to cover them. They are very well developed. And the more you come into regional or local effects, the more complex the system becomes. And all these impact in the impact assessment, there are no physical units, yeah, you can easily measure. They are all very complicated. I would not call them artificial, but somehow they are artificial to need big models to determine the CO2 equivalents or the particle equivalents. But anyway, different impact categories and the global ones can be covered quite well. Um, it's also seen here that LCA methodology is best suitable for global impacts, a little bit less for local impacts. And the so-called endpoint indicators, if you have three or only one, I think they're very questionable. You have to reduce everything to one number. It's really summing up the table. We've seen the two green and the two red numbers. That's maybe too. But anyway, the minimum impact from bioenergy or biofuel side is to look on greenhouse gas emissions and primary energy. That's a must. And at least also land occupation is also relevant. So if you make a serious LCA on biofuels, this is a minimum that should be covered anyway. Steps in the future, as I told you, we are working on climate neutrality and circularity potential. We have developed a definition which is not so broadly accepted at the moment, but we hope that in future this will set a new landmark, also judging on circularity and climate neutrality. So this was it on the topic of impact assessment. And if you have any questions, just ask me.
Good afternoon, sir. So my question is it really necessary to quantify sustainability in a single number? Because I think numbers just give us just open doors to new questions. So why we are after getting a single value for sustainability? Let them be like multiple values. What's problem in that?
Yes, I fully agree with that. So because the system is so multidisciplinary, we need more and more indicators. Yeah, I fully agree. Very good final remark.
Uh, Thank you for again a very nice lecture, nicely synthesized. And at least I think participants, though modeling and all those, they might not be so much understandable at this point. But I think the take-home message, whatever you have shown in a figure, it is uh, very penetrating. I would say that they will be able to understand whenever they are doing some research of their interest, that what will be its impact locally, regionally, and globally. So that point, I think they will be able to incorporate at least in their introduction and discussion part. So it will help them, and then definitely if they are doing detailed analysis, LCA analysis on that, for that definitely they need a lot of data. And yeah, we really look forward to see the different, learn about different databases which are available there, that so that they can really work on the things for which they need primary data, or they need to collect primary data on their own. And the secondary data, if it is available, then it's always a plus point for them. Yeah, so thank you very much for the nice talk. And maybe we can yeah, when we will be giving them the exercise, the group task.
I can start to explain it today or tomorrow. Yeah.
Yeah, tomorrow morning we can take it up. Yeah.
Yeah. So I can plan it maybe tomorrow morning on the very
Yeah,
beginning. I
yeah.
explain it to you, then you are fresh to absorb what your homework is, and prepare for tomorrow afternoon a little bit time that you can work on it. Yeah, but let's do it tomorrow morning.
Thank you. Thank you. Thank you. So today evening we will be having a short trip to nearby hilltop, I would say, and a small temple is there. So we'll be going there, and without taking break, we'll be continuing with next session, which will be taken by